We now start our discussion on module number 3 of chapter 2. We have already seen the definitions of Lebesgue measurable sets, and we have seen that they are nearly open or closed. We have established their various properties and have seen that the Lebesgue measurable sets form a sigma algebra, and in other words, the collection of Lebesgue measurable sets is quite a large class of sets. In particular, we have seen that open sets, closed sets, F sigma sets, G delta sets and Borel sets are Lebesgue measurable. So, we have many examples of Lebesgue measurable sets, but still we do not have any example of a set which is not measurable. So, in this module what we are going to do is that we are going to construct a set which is not measurable, and for that we are going to use axiom of choice. To show the existence of a non-measurable sets, we need to use axiom of choice. Recall what is axiom of choice? Axiom of choice says that given a collection of sets, we can construct a set by taking one element from each set. Obviously, if the sets in the collection are pairwise disjoint, in that case we will take distinct elements from each set, and the cardinality of the resulting set will be equal to the cardinality of the class of sets. Now, consider the interval closed 0 1 open, where we define a binary composition plus dot, we call it sum modulo 1 as follows. For x y two numbers belonging to closed 0 1 open, we define x plus dot y equal to x plus y if x plus y is less than 1, and x plus dot y is equal to x plus y minus 1 if x plus y is greater or equal to 1. So, what we actually do is that, see, closed 0 1 open is not closed under the general addition operation, but if we consider the sum modulo 1, then closed 0 1 open is closed under this operation, because whenever the sum exceeds 1 or is equal to 1, we subtract the number 1 from the sum, so that the x plus dot y again belongs to closed 0 1 open. For E subset of closed 0 1 open and an element x belonging to closed 0 1 open, we define the translation of E modulo 1 by the element y just as E plus dot y equal to collection of all x plus dot y, where x belonging to E. We first prove this result, which we will use to construct the non-measurable set. If E subset of closed 0 1 open is measurable, then E plus dot y, that is the translate of E modulo 1 with respect to the number y, this is also measurable for all y belonging to closed 0 1 open, and further mu of E is equal to mu of E plus dot y. So, the measure also does not change. We start the proof. Let us write E1 equal to E intersection closed 0 1 minus y open, and E2 E intersection closed 1 minus y 1 open. So, we divide the whole interval into two disjoint parts and take their intersection with the set E. Obviously, since E is measurable, so E1 and E2 are pairwise disjoint measurable sets, and E is the union of these two pairwise disjoint measurable sets E1 and E2. Consequently, by the additivity of Lebesgue measure, we have mu of E equal to mu of E1 plus mu of E2. Now, see that since E equal to E1 union E2, so E plus dot y is equal to E1 plus dot y union E2 plus dot y. Now, if we recall the definition of this sum modulo 1, see that E1 plus dot y is actually equal to E1 plus y, because the sum does not exceed 1, and E2 plus dot y is actually equal to E2 plus y minus 1. So, I can think of the translates as usual translations with respect to the usual addition operation. In the first case, we consider the translation of E1 with the number y, and in the second case, we are considering the translation of the set E2 with respect to the number y minus 1. Since E1 and E2 are both measurable, so from the fact that translates of measurable sets are measurable, it follows that E1 plus dot y and E2 plus dot y are also measurable. Also, we have seen that under translation operation, Lebesgue measure remains invariant. So, mu of E1 plus dot y is equal to mu of E1, and mu of E2 plus dot y is equal to mu of E2. Now, we claim that the sets E1 plus dot y and E2 plus dot y are disjoint. Why? Because otherwise, if we take a point Z in the intersection, then by definition this point Z looks like E1 plus y, since it belongs to E1 plus y, and at the same time it is of the form E2 plus y minus 1, where E1 and E2 belongs to capital E subset of closed 0 1 open. But this implies that E1 is equal to E2 minus 1, but this is less than 0. So, E1 cannot belong to the closed 0 1 open, which is a contradiction. Hence, E plus dot y being the union of two measurable sets is also measurable, and obviously mu of E plus dot y, this is equal to mu of E1 plus dot y plus mu of E2 plus dot y, and this is equal to mu E1 plus mu E2. We start by defining a binary relation on the set closed 0 1 open in this way. For two numbers x and y belonging to closed 0 1 open, we say that x is related to y if and only if the difference x minus y is a rational number. Now, observe that for any number x, obviously x minus x is equal to 0, which is a rational number. So, this relation is reflexive. If x is related to y, this means that x minus y is a rational number, and then y minus x is also a rational number. So, x is related to y implies that y is also related to x. Finally, for three elements x, y and z, if x is related to y and y is related to z, this means that x minus y and y minus z are both rational numbers, and subsequently x minus z is also a rational number, and so we have x related to y, y related to z implies that x is related to z, and so this relation is also transitive. In other words, we have the fact that this relation is an equivalence relation. Now, we know that whenever we have an equivalence relation on a set, it partitions the whole set into disjoint equivalence classes. So, this particular equivalence relation also partitions closed 0 1 open into disjoint equivalence classes. Note that for two elements x and y, they belong to the same equivalence class if and only if their difference is a rational number, and they do not belong to the same equivalence class if and only if their difference is an irrational number. Now, we can apply axiom of choice. By axiom of choice, what we do is that from each equivalence class, we pick up one and only one element and construct a set capital P. Obviously, this set capital P is subset of closed 0 1 open. So, we have constructed a set capital P subset of closed 0 1 open by taking one and only one element from each equivalence class. We will see that this particular set P is actually non-measurable. For this, we start with the sequence of all rationals in closed 0 1 open. Let R n equal to 0 to infinity be a sequence of rationals where we take R 0 is equal to 0. Define P I as P plus dot R I for all I, that is, we take the set P and take the translate modulo 1 of this set P with respect to each of the rational numbers in closed 0 1 open. We claim first that the sets P I have this property that their whole union, that is union I is equal to 1 to infinity P I, this is the whole interval closed 0 1 open. And the second assertion is that for I not equal to j, the sets P I and P j are disjoint. we start with our first assertion. Let x be any arbitrary point of closed 0, 1 open. Since closed 0, 1 open have been partitioned into disjoint equivalence classes, so this point belongs to some equivalence class. Note that the set capital P contains one and only one element, say small p, from each equivalence class. So, it contains one element from this particular equivalence class. This means that x and small p both belongs to the same equivalence class, and consequently the difference x minus p must be a rational number. Now, if x is greater than p, then we can write x as p plus x minus p, where x minus p is a rational number. So, it belongs to p plus dot r I, where r I is taken as the rational number x minus p. If x is less than p, then we can write x in this form p plus x minus p plus 1 minus 1. See that x minus p plus 1 again is a rational number which belongs to closed 0, 1 open. So, this belongs to again capital P plus dot r I, where we take the rational number r I as x minus p plus 1. So, in any case the point x belongs to some p I, and this shows that the union of all the sets p I should be closed 0, 1 open. Next, we prove our second assertion that for I not equal to j, p I intersection p j are disjoint. If not, then take a point z belonging to p I intersection p j. Now, see that when we say that I is not equal to j, evidently r I is not equal to r j, that is r I and r j are two distinct rational numbers in closed 0, 1 open. Again from the definition of the translate, z is of the form p 1 plus dot r I, as well as z is of the form p 2 plus dot r j for some elements p 1 and p 2 belonging to capital P. But see that p 1 plus dot r I is equal to either p 1 plus r I or p 1 plus r I minus 1, and p 2 plus dot r j is equal to p 2 plus r j or p 2 plus r j minus 1. So, in any case, since r I and r j are rational numbers and 1 is also a rational number, so if we consider the difference p 1 minus p 2, then p 1 minus p 2 must be a rational number, and so it should belong to some equivalence class, because we have seen that two elements belongs to the same equivalence class if and only if their difference is a rational number. So, p 1 and p 2 must belong to the same equivalence class. But capital P contains one and only one element from each equivalence class. So, p 1 and p 2 cannot be different. So, the only thing possible is that P1 should be equal to P2. But if P1 is equal to P2, then from above we see that either Ri will be equal to Rj, which is not possible because we have already assumed that Ri is not equal to Rj. Otherwise, Ri will be equal to Rj minus 1 or Rj will be equal to Ri minus 1. But again see that since Ri and Rj both belong to closed 0 1 open, Ri minus 1 or Rj minus 1 are negative. So, cannot belong to closed 0 1 open. So, this is impossible. Hence, this proves our second assertion also. Now, on the contrary, assume that the set capital P is measurable. Now, see, we have already shown you that if P is measurable, then all its translate modulo 1 are also measurable, and closed 0 1 open is the union of all these Pi, which are again pairwise disjoint. So, by countable additivity of the Lebesgue measure, we get 1 equal to mu of closed 0 1 open. This is equal to sigma I equal to 1 to infinity mu Pi, but this is equal to sigma I is equal to 1 to infinity mu P. We have already seen that mu of E plus dot x is equal to mu E for any measurable set E. So, each mu Pi is equal to mu P. So, we are adding a constant number, infinite number of times, and the result is that on the right hand side we will get either 0 or infinity according as the measure of the set P is 0 or measure of the set P is greater than 0. So, in a nutshell, we have a relation like this, that 1 is equal to 0 or 1 is equal to infinity. But you know that this is impossible. Why we have come to a contradiction? Because we have assumed that the set capital P is measurable. So, this shows that the set P must be non-measurable. So, this proves the existence of a non-measurable set. We are now going to show that the Lebesgue outer measure is not countably additive, and for this we have to take the help of the non-measurable set P, which we have defined. Just recall that we had defined a binary relation on closed 0 1 open, and this binary relation is an equivalence relation on closed 0 1 open, which partitioned the whole interval into disjoint equivalence classes, and by taking one and only one element from each equivalence class, we have constructed a subset capital P of closed 0 1 open, which we have shown to be non-measurable. We have also shown that if Rn is the sequence of rational numbers in closed 0 1 open, then we can construct the translates of the set P with respect to these rational numbers, which we have denoted as Pi, which is defined as P plus dot Ri. We have shown you that these sets Pi are pairwise disjoint and their whole union is closed 0 1 open. Now, consider the set P. We have already shown that it is not measurable. So, if we consider its Lebesgue outer measure, then mu star of P cannot be equal to 0, because we already know that a set of Lebesgue outer measure 0 is always measurable. So, mu star P should be positive. If mu star P is strictly greater than 0, since mu star of Pi is equal to mu star of P for each I, so mu star of Pi is greater than 0 for all I. Now, if we consider the fact that closed 0 1 open equal to union I is equal to 1 to infinity Pi, then we have, so 1 equal to measure of closed 0 1 open, which is strictly less than sigma I is equal to 1 to infinity mu of Pi, which is equal to sigma I is equal to 1 to infinity mu P, which is actually equal to plus infinity. So, to summarize, what we did in this module is that we have finally defined a non-measurable set with the help of axiom of choice. See that we have defined the non-measurable set inside closed 0 1 open, but we can take any interval closed a b open and do the same thing. So, each interval in the real line contains a non-measurable set. So, there are many non-measurable sets, and finally, we have shown that the Lebesgue outer measure is not countably additive, and with this we finish this module.